So I think we can start. We're a little late, but nonetheless we can start. So we were talking about sampling, and till now we have talked about three types of sampling algorithms. What are those? First one is the inverse CDF or reverse sampling, where the idea is that you will sample from uniform and then use the inverse CDF to transform it into the distribution or the target distribution or distribution of interest. That's the most basic one. The problem, however, is that in our case, the CDF or the PDF is not known, like the posterior is not known. It is only known up to a normalizing constant. We only know likelihood and prior. You can multiply, but we will never know the evidence, right? Then with that motivation, we started talking about sampling methods that can be used for Bayesian machine learning. And in that context, the first algorithm we discussed was the rejection sampling, where the idea is that you sample from some proposal and then accept or reject based on certain criteria. And we have proved that whatever sample you accept follows the target distribution. The problem, however, is that many samples get rejected, and as a result, it is very, very slow. That is the second thing we have talked about. The third thing that we talked about in the last lecture was the importance sampling. And in importance sampling, the idea is that we don't want to reject anything. So we use all the sample, but in a weighted manner. So we give weights, and based on the weights, we do it, and we saw that how to compute those weights. But importance sampling or the vanilla importance sampling is not applicable to Bayesian or where unnormalized distribution is given and a normalized distribution is not known. And so we talked about normalized importance sampling, which can handle Bayesian inference and the kind of things we encounter in this course, right? So these are the things we have talked about till now. So let me just quickly write it down. So the first thing we have discussed. So we have discussed three sampling schemes till now, right? The first one is the reverse sampling or inverse CDF based on inverse sampling, inverse CDF based sampling. And here your x is equal to fx inverse of u, where u comes from some uniform distribution 0, 1, right? This is the inverse CDF. Fx inverse is the problem. The second one that we have talked about is rejection sampling, and here to very quickly write down the algorithms. You sample x from some proposal which you decide based on certain criteria. You also sample u from uniform 0 and 1, and then if pi of x divided by mq of x is, if u less than equal to, actually sorry, so let me write it down. This will become greater than equal to in that sense. Greater than equal to u, then you accept, else you reject, right? And you accept with a probability, and the probability is the ratio that you see in the top, right? Again, we have discussed it. The third one that we have discussed is the importance sampling. Importance sampling, and here the idea was that we are interested in computing expectation. Always what we are trying to compute is the expectation, and in importance sampling, expectation with respect to pi fx is equal to integration of to directly write down the formula. Wx fx qx dx, which is basically equal to expectation with respect to q wx fx. And this we saw last time how we derive it. It's simple, divide by pi q, multiply by q, and then just make adjustment, and you will get it. These are the three things we have discussed, right? Nothing new. Now, can you tell me what is common in all of these three schemes we have discussed? Is there anything that is, or specifically the last two schemes? First scheme you forget about. What is common in rejection sampling and in importance sampling? Is there something that is common? Proposal is there, right? Anything else? Proposal will be there throughout. Anything else? What are these things they were based on? Remember, all of these things that we are discussing is based on the law of large number. So the basic thing that connects all of these things is the law of large number, right? So whatever sampling algorithm we have discussed till now is based on the law of large number, right? Only then you know that if you take the mean, you will get the mean. All of this is based on the law of large number, right? So all the things, or not things, algorithms, all the algorithms discussed till now uses or relies on the law of large number, right? And what is the law of large number? It says that if you draw samples which are IID, then if the number of sample increases, you converge towards the mean. That's what it says, right? If you draw samples and compute the mean, the sample mean will converge towards the actual mean you are trying to estimate, and as the number increases, you can get the exact value almost surely. There is a strong law of large number. A weak law of large number will represent the same thing but in a probabilistic sense, right? So now there is a problem here. The problem here is that the law of large number is based on the independence assumptions. If the samples are not independent, then the law of large number is not valid. And in that case, you cannot say that the mean will converge towards the mean or the distribution will converge towards the distribution. That you can no longer say, right? So that is the major bottleneck. So a major bottleneck in all of this algorithm is that it necessitates generation of independent samples, okay? Because that is the law of large number demanding. Now, why is this a bottleneck? Why is generating independent samples a bottleneck? Because in computers, as you are generating, you are fine. But if you have to generate numbers, or if you have to work with numbers or samples which are generating naturally, then the independence assumption might not hold. For example, you can collect data of weather. You collect data of hourly data, let's say, hour 1, hour 2, and like that, let's say you collect it for 20 days. Do you think these samples are independent? They are not, because whatever is happening in this hour is dependent on what has happened earlier, right? So in reality, if you try to work with samples, those samples will not be independent. And as a result, if the samples are not independent, the sample mean representing the population mean, that whole thing breaks down. This is true for most of the things you can imagine where real sampling is needed. Example, let's say election survey. If you start sampling persons, obviously if there is a family, those samples are not independent, right? Because they will probably have a tendency and some dependency towards whom they are voting. So samples generated in reality are often not independent. And as a result, if you want to use law of large number there, it will create a problem. Okay. So this, as I said, LLN necessitates independent samples. And this is a bottleneck in many cases. Okay. This is a bottleneck in many instances. One example that I gave was the weather data. Weather data is always dependent. It has to be dependent. Okay. So that is the problem. So, and by the way, the law of large number is very old. It was proposed by Bernoulli in the year 1760 or something like that, 62 or 60. So that is the time when the law of large number was originally proposed. And then for around 150 years, no one touched it. Everyone was working with the law of large number as proposed, which is for independent trials. In 1890s and towards the end of 1800 and the starting of 1900, a question became the talk of the town or talk among the researchers, which is, can we apply law of large number to dependent samples? So this was a huge question in the late 1800s and early 1900s. And this question came into the forefront because of rivalry, intellectual rivalry, I will say, of two researchers. One of that was Markov. The other name I forgot. Okay. So Markov chain I am talking, so Markov name I remember, the other name I don't remember. They are from the same universities and they wrote a series of papers on this law of large number for dependent samples between 1890, 91 to 1907, 8 in that time. So for that 18, 19 years, they were writing series of papers, one rebutting the other. So one is saying that this is correct, he is saying no, that is wrong, and he was providing proofs. It's not like a fight. It was intellectual rivalry, as I said. So they were giving proofs. And during that time, Markov came up with the law of large number for dependent samples. It is something different and it is based on the Markov chain, which we will discuss today. And hopefully by the end of this today's lecture, we will see that what does it even mean. Okay. But ultimately the idea is that you want to sample from a distribution. That is the ultimate idea, right? Okay. So when I say samples are I mean, samples are independent, right? In law of large number, I said that the samples are supposed to be independent. What does it even mean? It means that if I have to, just for clarity, I think most of you should be aware of what does it mean. But say I have a distribution like this. Okay. So this is some PDF. Okay. And suppose I have one sample here, let's call it x1, and I have another sample here, x2. Okay. Now from this PDF, what can we say about x1 and x2? Can we say something about x1 and x2? Yeah. x2 is more likely than x1. x2, the chances of getting x2 is more probable, right? That we know. But suppose I am drawing a sample and by some chance the first sample comes out to be x1. Will my conclusion change about x2 and x1 once I have observed x1? No. If it does not change, then that is known as independent sample. So that means even if I have observed x1, I should still be able to say with certainty that probability of getting x2 sample is more than getting x1, and not only more, the more if I quantify, that should also be same, like the ratio of the frequencies would also be same. If I can do that and say that, then it's independent, because given that x1 has observed, the chances of getting x2 or does not change. So they are basically independent. Okay. So if samples x1 and x2 are independent, then observing x1 as the, let us say, Th sample will not change my belief about observing x2 while in the t as the t plus 1th sample. And in a very basic sense, that's what it means. That's what independence means, that whether something has happened or not should not influence what is going to happen next, right? Now, if you think carefully, the example I gave where I said that samples I get are not independent, you will realize that most of those cases are time series data. So generally in time series data, the samples you draw are not independent. I talked about weather modeling, that's a time series. You can think of any time series and you will realize that it does not happen. And for specifically for those who are from mechanics background or who knows some basic differential equation, you know that when you solve differential equation, yt plus 1 is dependent on yt, be it a stochastic differential equation or ordinary differential equation. So naturally yt plus 1 is dependent on yt. So that means if your initial condition changes, the next samples things start changing. And if it is a chaotic system, slight change will result in huge changes. Okay. So generally in time series data, samples are not independent. Okay. And so I will be discussing the Markov chain and this law of large number for dependent variables in the context of time series only. Okay. So because that is where you will observe it. And even if it is not a time series, as you will see later, like in your Bayesian inference and all those things, even in that case, we will create a virtual kind of time series. We will call it Markov chain. And chain means there is a time, not exactly, but you can think of it as a sense of time we are imposing forcefully on a thing. Okay. And that we will do, but that too is not today. Today we will only talk about Markov chain, we will not talk about any sampling. Okay. So now, with that background, let us start talking about Markov chain, or let us start talking about what does it even mean. So, suppose I have a variable, not just any variable, random variable, and the random variable is obviously random, that is why we are calling it random variable, but it is also changing with time. For example, weather. Okay. For example, any time series, stock market, any time series you can think of is like that. Okay. So we are going to consider a random variable, but the random variable is not just any random variable, it is a random variable that changes with time. And such a random variable is known as random process, because it is not only now random, but it is also a function of something else like time in this case. Okay. So consider a random variable that evolves with time, And such a random variable is generally denoted as x t omega. This is the general notation, and actually this is not called a random variable, it is called as random process. Okay, t can be x also, it will still be random process, or random field is another name that is used, but it is still the same. So the idea is that x is not only random, omega denotes that it is random, but it is also function of t, and that is denoted by the, it is also function of time, and that is denoted by the factor that the t is there in the bracket. Okay. So basically this indicates randomness, and this indicates time. Okay. So x changes with time, and it is also random. That's what it means. Clear? So now, with this background, let us also assume, but let me first write that such variables are called random process. Random process, or sometimes random field, but if it is a field, then generally t should be replaced by x. Yeah. Omega and yes. So very simple. Consider y as a sine omega t. I'm just giving an example, right? That's a time series. Now assume omega to be random. So what will happen to y? Y is a function of time, but y is also function of random variable. So in that sense, there is some random variable that is influencing it, and there is some time variable that is influencing it. That's what it means. Why do we write it like that? Because as I said before the starting of the class, that random process is like infinite collection of random variables. So all those random variables are coming from some probability space. So in that probability space, omega resides in that probability space. So in that sense, okay. And y is equal to a sin omega t is example that helps us relate with this thing. It's not about one omega or something like that, or both are omega, so nothing to do with that, but it just helps you relate with things. Okay. So such variables are called random process. Now to make things simpler, we will assume that we will assume and work with discrete valued random process. Okay. So we will work with, so we also consider x t semicolon omega to be a discrete valued random process. Discrete value random process, yeah, that's right. Now what does it mean? Can someone tell me what does it mean, discrete valued random process? Random variable is discrete, but it's changing with time. So what will happen? Time is continuous, right? So at each time, what you will get a discrete output. Yeah. So what the sample at each time is you are getting, but time is continuous. For example, it's very simple. Suppose I'm looking at weather, but I don't want to look at the temperature. I want to classify it as extreme hot weather, mild weather, or pleasant weather, and cold weather. Now at each hour or each day or each month, you will say the weather was either extremely hot, pleasant, or cold. I'm not saying extreme cold because we don't go to negative here. So if I was giving it, staying in USA, I would have given the example of extreme cold, but here I think that's not valid. Okay, but so each sample at each time will be one of these four. In that sense, it will become it is an example of discrete valued random process. So the weather is changing, but if you fix time, you will get one of these four, or you will get probability for each of these four. Clear? So that's an example of discrete valued random process. If it was a continuous value, then you just look at temperature. It will take some continuous value at each time. And that is random, obviously. So then it becomes continuous valued random process. Clear? Okay. So we also consider this to be a discrete valued random process. So basically, let's assume x t semicolon omega has 4 states S1, S2, S3, S4. What is S1 here? What does state means? State means outcome of the random thing. So what will be an example of S1? In the example I gave, S1 can be extreme hot, S2 will be hot, S3 will be pleasant, S4 will be cold. So how is the weather? And then let's say you ask me, or you ask someone, or I ask you that what is your belief, or what do you think is the weather going to be in October 30th? You will say, I think S1 will be 0.05 because it's not going to be very hot, very unlikely. S2 will be 0.15, that chances is more. S3 pleasant, that will be 0.75, and whatever remaining is S4. That will be your belief. So that means each of these will have a probability, and sum of those probability will be equal to 1 for a given time. Clear what is happening? So that means if I have to draw it and show it, it will seem something like that. So let's say x at t equal to t0, let's denote it as x0. Okay, that's a notation we are going to use. It means x is the random process, remember that. So it's still random. I'm not writing omega, but it's random. And at t equal to t0, whatever I'm getting, I'm denoting it as x0. Okay. So maybe it will look something like this. So let's say this is my S1, this is my S2, okay, then this is my S3, and this is my S4. What are these bars representing? These bars are representing the states, probability of the states. Okay. So basically it is representing that the probability of getting S4 is more at T0 as compared to S3, S2 and S1. S2 is the second likely one, S1 is the third likely one, S3 is the least likely one. So that's what it is denoting. Okay. So this is at a given time T0. Now let us change the time. What do you expect if the time changes? What will happen? What will be your belief be if I ask you that, okay, tell me about the weather next April? Obviously that probability will change. You will say most likely it will be hot. Extreme hot is also a possibility. Cold is not a possibility. Pleasant if you are very lucky. That's what he will say. That means this belief evolves in time. Whatever state you can expect changes with time, right? So if I take x at t equal to t1 is equal to x1, then these things will change, but the outcome is still 4, because I have assumed that it's a discrete value and it can give only one of the 4 states. That's the assumption we are working with, right? So maybe at this stage your S1 has reduced, your S2 has also reduced, S3 has also reduced, and your S4 has skyrocketed. Obviously, the three thing reduces, one has to increase because the total has to be equal to 1, right? Now, I am not drawing, but you can also think about drawing x2, x3, xt. You can keep on drawing those, and these things will obviously keep on changing. Okay? Clear? What is happening? Things are evolving in time. The states are changing in time. So now, one of the question is that, okay, we understand that for a random process, discrete value random process, the probability of states will change with time, correct? Even for a continuous value, the probability of states will change with time, but I cannot write this discrete form. I have to then draw the continuous PDF, correct? But how are these changing? If I have to track, how are these changing? What do you think we can do? So we acknowledge that it is changing, but we also want to track, because if we have to use it for solving some mathematical aspects or mathematical problems, we need to track how is it changing. So what do you think influences this change? Time. Definitely time influences. Anything else? W, obviously, but W is not explicit, right? W is obviously there, but it is implicit, so you cannot do that. So time is a correct answer. Time influences, but we are not explicitly working with time. So what we can say is that whatever happened in the previous state should influence what is happening next. Case in point, if today I see that the weather is hot and cloudy, probably I can expect some rain tomorrow. So the
doesn't happen in every case.
It doesn't happen because that's why there is a probabilistic aspects. If it was certain to happen, then I would have made it probability equal to 1, but I am not doing that. So there will be some probability as probabilistic aspect is there, but I can say that if, let's say, there are 10 days I have observed in a year where the weather was hot and cloudy, then maybe out of those 10 days, 7 days it will rain the next day. So that means my belief about raining next day is 0.7, given that the weather today is hot and cloudy. Other beliefs can also be there, but it's all in a probabilistic sense. But it definitely influences. It is very unlikely that the weather today is hot and cloudy and tomorrow it will be -5 degrees. It won't happen, right? If it is supposed to be -5 degrees today, at least you will see that weather today is maybe 5 degrees plus, not plus 30 degrees, right? So the hypothesis is that, and I am talking it as a hypothesis because you will soon realize why I am calling it a hypothesis. But the hypothesis is that right now, that whatever I am observing, my belief about the state at time t is influenced by my belief about the states at time t minus 1. Whatever my belief is today is influenced by whatever it was tomorrow, or whatever my belief is about tomorrow is influenced by what I am seeing today, right? So one aspect one factor that influences the probability of a state at time t is what you have observed at t minus 1, right? It's logical to assume that it's based on our observations, and it definitely happens, right? Again, going back to the mechanics thing, it surely happens because yt plus 1 is equal to some function of yt, right? Any numerical integration, you will realize that yt plus 1 is a function of yt. So it definitely happens in differential equation, right? Obviously, the differential equation I am talking about has no randomness, but there can be randomness. There is the SD whole domain of SD where there is randomness, and still it happens. Okay. So now, because it happens, we can think of it in this manner. So suppose I have x0 here, and at x0 suppose I have observed S1. So S1 has been observed. So at x0 equal S0 is observed. So that has happened, right? So then at x1 I can observe either S1 or S2 or S3 or S4. One of these four I will have to observe, right, for my problem. And given that S1 has been observed, each of these will have a probability. Okay, each of this will have a probability. So the first arrow will denote what is the probability of observing S1 at time t1 given S1 has been observed at time t0. That's what the first thing is denoting. Let's give some number. Let's say it is equal to 0.4. This is equal to 0.2. This is equal to 0.1. So 4, 2, 6, 7. So this has to be equal to 0.3. Okay, and the summation should be equal to 1. Okay, so from this diagram, for example, one of the observation is that probability of observing S1 at T1 given S1 has been observed at T0 is 0.4. That's what the diagram is telling me, correct? Now it might be possible that at x0 I have not observed S1, I have observed S3. That's also a possibility. So let's say again at x0, okay, let me draw here only. Let's say I have observed S3. Right? Now given that I have observed S3 at T0, the probability of I might look into probability of observing S1, S2, S3 and S4, right? But these probabilities, will it be same as before, or do you think they will be different? Different, because given that my belief at x0 has changed, my belief at x1 should also change, right? So let's call it, let's give some number now. I don't know, let's maybe 0.1, 0.7, 8, 0.15, 0.05. Okay. I hope the summation is equal to 1. I think it is, so that's fine. So that means from this, what can I say? Let's say one statement, let us take the probability of observing S2 at T1 given I have observed S3 at T0 is equal to 0.7, right? Another statement is that probability of observing S2 at T1 given S3 at T0 is 0.7, right? This is another observation just from the diagram I drew. Now, what are these numbers denoting? Probability, but what probability? What are these numbers denoting? Definitely they are denoting the conditional probability, but they have a name. This is known also as the transition probability, because this is giving you the probability of transitioning from a state to another state. So, these probabilities, these numbers denote the transition probability, because this is saying you with what probability will like it is with 0.7 probability that you will transition from S3 at T0 to S2 at T1. If I rephrase this sentence in sky, that's also a valid statement, that it is with probability 0.7 that I will transition from S3 at T0 to S2 at T1, right? So, these probabilities are known as the transition probabilities. So, these are known as the transition probability. Okay, these are known as the transition probability, and obviously you can understand that this kind of representation I have shown is very cluttered. I mean, even with 2 it's almost quite cluttered. If I have 10 states, it's very difficult to represent, right? So that's why this is not a standard representation. We represent this transition probability in one of the two ways. One is you can either draw the transition diagram, state transition diagram, or you can have the transition matrix. Transition matrix is what we use in programming and coding and all those things. Transition diagram is a graphical representation. Okay. So, transition probability, is are represented using state transition diagram or transition matrix. Okay, and it's a matrix because we are in discrete. In continuous it will be something else. Yes.
Are these also the probabilities of states appearing at that time step?
No.
This transition.
This is transition. This is not the probability of state at that time. It is the probability that you will observe S2 given you have observed S1. So these are conditional probability, not the marginal probability.
Those will be different.
Those will be different. Those have to be computed, and we'll do that soon. Okay. So these are all transition probability. So these are conditional probability, which means these are only giving you probability of transitioning. These are not the probability of the states. Okay. So now let us first draw this transition diagram. So let's say I have S1, S3, S2, S4. Okay. Now, if I take the same diagram of S1 and S3, I know that from S1 and S3 you can transition to any state with a finite probability, right? If from S1 you can go to S1, S2, S3 and S4, and with a finite probability, not a zero probability. So that means from S1 you should have arrows like this. So from S1 to S1 you can go, S1 to S2 you are allowed to go, S1 to S3 you are allowed to go, S1 to S4 you are allowed to go. What is the probability of going from S1 to S1? 0.4, 0.2, 0.1, 0.3. So 0.4, 0.2, 0.1 and 0.3, right? This is coming from this diagram only. Okay. Next, let us first draw S3, because S3 is also here. I have to copy paste. Other numbers I will reassign randomly because I have not shown it. So from S3 also you can go to any state. So let's say from S3 to S3 you will have a probability. S3 to S2 I think is 0.7. S3 to S1 you can go, and S3 to S4 also you can go. I forgot the number. S3 to S3 is 0.15. This is 0.7. S3 to S2 is 0.7, right? S3 to S1 is 0.1. This one is 0.7, and I think last one is 0.05. Okay. Next, let us come to S2, and let us assume that from S2 you can only go to S4 and to, let's say, S1. Okay. So basically that is also a possibility. There is no compulsion that from a state you have to go to all the states with a finite probability. Okay. So only two states you can go, from S2 to S4 and S2 to S1. So whatever arrow is missing, that means those are having zero probability of transition. So whatever probability is zero, you don't draw arrow for that. That's the notation. Clear? So let's say this is equal to 0.5 and 0.5. Okay. Lastly, I am at S4, and let's say from S4 I can go to either S4 with 0.3, or I can go to S1 with 0.7. Okay. So this completes my transition diagram, a representative transition diagram, which is only for your understanding. You cannot use this in, let's say, programming or something like that, because for programming you have to work with the transition matrix, which I am coming next. Okay. So now the same thing can be represented as a transition matrix. So let us see how you can do that. So let's say we now want to write transition matrix. So you want to transition from S1, S2, S3, S4 to S1, S2, S3, S4. So your matrix will be a 4 cross 4 matrix. In this case, or in a generic sense, it will be K cross K, where K is the number of states. So let us write S1, S2, S3, S4, S1, S2, S3, S4. Okay. What is the probability of going from S1 to S1? You tell me. 0.4. S1 to S2. 0.2. So that should be, you see, so a row is representing where you are, a column is representing where you are going. So that's the notation, remember that. A row is representing where you are, a column is representing where you are going. What is S1 to S3? 0.1. And S1 to S4? 0.3. S2 to S1? 0.5. S2 to S2? S2 to S3? 0. S2 to S4? Okay. S3 to S1? 0.1. S3 to S2? 0.7. S3 to S3? 0.15. S3 to S4? 0.05. S4 to S1? S4 to S1 is 0.7, right? Rest are 0, and this one is 0.3. So what is your observation from here? Each row should sum up to but the columns need not sum up to 1. This is not a symmetric matrix as we often encounter. Okay, this is, and there can be many zeros. In this case there are not, but in most cases you will find many zeros in this, because you are often restricted that from this state you cannot go to some of the states. Okay, so this is known as the transition matrix. Okay, let us generalize it. In a generalized setup, the transition matrix is represented as P. Okay, that's a common notation, capital P. Capital P is equal to rho 1 1, rho 1 2, and assume that I have k states, so rho 1k, 2 1, rho 2 2, rho 2k, rho k1, rho k2, rho kk. Okay, where what is rho ij denoting? Can you tell me what is rho ij denoting now? From I to j. So, and not probability that at x equal to t plus 1 you are at jth state, given that, right? This is what it is denoting, that probability of transitioning from I to j as you go from t to t plus 1, right? Clear? So, this is your transition matrix in a generalized form. Okay. Now, let me quickly introduce the Markovian Markov chain actually, or the Markovian assumption that is inherent here, and then I will go to some mathematical aspects. Okay. So, Markov chain, right? So, basically in all of this I have assumed something like this: x1, x2, and this notation I have already introduced. X1 means x at time t1, x capital T. Okay. So, this kind of diagram, when you see, it is known as the Markov chain. This is the Markov chain representation. Okay. What does it mean? It means that probability of xt is only dependent on xt minus 1. Probability of x2 is only dependent on x1. Okay. So, this is a Markov chain, and this basically is equivalent to saying, probability of xt given x1 to t minus 1. 1 to t minus 1 means x1, x2, x3, dot dot dot, xt minus 1. This is equal to probability of xt given x t minus 1 for all t. This is what it means. So, whatever is shown in the diagram on the left basically means this equation on the right, which means that only your previous state is important to predict, or needed to predict, or to have some idea about the next state. Given that you know your previous state, everything else is conditionally independent. That is what it is saying, that given that you know the previous state, it is conditionally independent. Okay. So, they are not unconditionally independent. X naught has an influence on xt, but it is through x1, x2, xt minus 1. But if you condition on something, then it becomes conditionally independent. So, this is a classic case where, let us say, xt and x0 are conditionally independent but not independent. Okay. So, and by the way, this is not a generalized Markov chain. This is the first order Markovian assumption. So, first order Markov chain. Okay. So, this is the first order Markov chain. Why first order? Because only one is influencing. Okay. So, this is the first order Markov chain. What do you think you will get in a second order Markov chain? So for two states, previous two states will have influence. For second order Markov chain, you will get probability of xt given x 1 to t minus 1 will be equal to probability of xt given x t minus 1 comma x t minus 2, right, for all t. So basically the previous two steps will start influencing, but this is almost never used. We almost always work with the first order Markovian assumption. Okay, almost always. I have never seen higher order Markovian assumption being used. Maybe they are used in certain cases, but I have not seen. Okay. Now, why do you think first order Markovian assumption or first order Markov chain is preferred? Can you give me a logic of preferring first order over second order? Any easy to use in what sense? Computational cost. Why? Both of these are correct, but why? Not two multiplication, the number of parameters will reduce. The more things are independent, the number of parameters reduces. And as a result, it is easy and computationally easy. So both are correct answers. But the reason is the parameter, number of parameters reduces, right? So if it is, let's say this one, right? X, then it will not be a matrix. It will be a 3D matrix or tensor kind of thing. Because then you both will be have to condition on and you will get more number of parameters. Like in first order, you get k cross k. In this, you will get k cross k cross k. So naturally, number of parameters of the transition matrix will increase, right? So that is the reason. Because what was I doing? I was putting different values at xt minus 1 and looking at what values xt can take. So that's why k cross k was coming. Now I will put different values of t minus 1 and t minus 2. That itself is k square. And I will look what values it can take. That is another k. So k cube. So k cross k cross k, number of parameters will come in. Right? Clear? Clear? Okay. So this is the first order and second order Markov chain. Okay. So now, one question was asked earlier that what is the probability of observing a state? Right? What is the probability of observing, let's say, S1 at x1? How to compute that? What is the probability of observing the ith state given that P is known, given that P, which is the transition matrix, is known, given that P is known and the 0th state is known. Sorry, not 0th state, sorry, and the state probability of state at 0th time instant give a known and the probability of states at t naught are known. Okay. So let me repeat the question. So I have given you two information. One is the P is known to you. So this is known. Okay. The other thing that is known is probability of x0. So other thing that is known is probability of x0, which is equal to, I will write it as pi 0 transpose. Okay. So this is known as pi 0 transpose. What is pi 0 transpose? So let us write it down, where pi 0 is equal to pi 0 1, pi 0 2, pi 0 3, pi 0 4. Okay. Now someone explain to me what is pi 0 1. What is pi 0 1? Probability of state, which state? No, it's not a transition probability. Probability of state? Yeah, but you have 4 states, S1, S2, S3, S4. It has to one of those. So it is probability of state S1 at time t0. This is not a transition probability, this is at time 0. This is pi 0 1 is probability of observing state S1 at time t0. Pi 0 2 is probability of observing state S2 at time t0. Right? So let me write it down. This is equal to probability of observing S1 at t0. Okay. The others I am not writing, you can understand the others. Like the third one will be probability of observing S3 at t0. Right? So now what you have to find out? You have to find out probability of x1 is equal to some value, let's call it Si, let's say. So this is what you have to find out. Tell me, how will you find it out? Not difficult. You know the transition probability matrix, transition matrix, and you know this thing. What will be this be equal to? What will this be equal to? Correct. Product and sum rule will be used. Both will be used. So what will be it equal to? First, let us see. At S0, you know the value, right? So probability that at x0 you had the value Sj, and then probability that at x1 you will take the value Si, given at x0 you have the value Sj, and this should be done for all the Sjs. The simple application of sum and product law, right? So if you do the product, you will realize you will get x0 comma x1. You are integrating on x1, you are getting x0, x0 you are getting x1, right? Now tell me, what is this? Where will you get this value? From pi. Where will you get this value? From p. So known to you. So this you will get from pi. This you will get from capital P. Okay. This you will get from capital P. And finally, probability of x1 is equal to Si will be equal to pi naught transpose times P. That's what you will do. But I will remove this. This is what you will get. That means this product will not give you just one probability. This will give you probability of getting S1, S2, S3, S4. So this will basically give you all the 4 probabilities that you are interested in. Okay. So let me show it to you. If I write this one in summation form, you will understand what will happen. So tell me, I want to write it in summation form. So what is the first probability equal to? Take I equal to 1 maybe, j should be all the values. So let's take I equal to 1. So what will be this equal to? The first one will be pi 0 1 multiplied by p going from I to 1, because I said that S1, right? The second one will be pi 0 2 multiplied by probability of going from 2 to 1, and then third one will be equal to pi 0 3 multiplied by probability of going from 3 to 1, and like that for the fourth term. So this will be equal to pi 0 I multiplied by rho going from I to you are at I here, from I you want to go to 0 1 actually 0 1, and you want to go from 1 to I, plus pi 0 2, and you want to go from 2 to I, plus pi 0 3, and you want to go from 3 to I, plus pi 0 4, and you want to go from 4 to I, right? That's what you will get. So when you write it in this form, you get not only one but all of those, and that's why pi is in a row form. So row times column, it will get multiplied and added, and you will get all the values. Clear? And this pi p of x1 is nothing but equal to pi 1 transpose, right? So pi 1 transpose is equal to pi naught transpose multiplied by p. Clear what we are doing? Okay. This is actually the fundamental thing of Markov chain. So the idea is that, can we devise a p, can we design a transition kernel or kernel matrix such that pi 1 is equal to pi naught? So what we want to do? We want to design a p, a transition matrix, such that pi 1 will be equal to pi naught, pi 2 will be equal to pi 1, pi 3 will be equal to pi 2, and it goes on. I am coming to that. Okay. And the question is, why do we want it? Because if you can do that, then at each time, if you are sampling from different distributions, but those distributions will become same. So as a result, you will, if that pi is equal to your target pi, then you will start getting samples from your target distribution. Because the pi is now not changing, so that means whatever sample you are getting, although they are dependent, they are from the same distribution. So with that, those samples, although they are dependent, they are now representing this distribution that you want. This is the law of large number for dependent. Basically, you can, even with dependent samples, you can draw samples from a same distribution. So basically, generalizing, I can write pi of t transpose time p is equal to pi t plus 1 transpose. Okay. If for a given p, pi of t plus 1 transpose is equal to pi of t transpose, then we call it the equilibrium distribution or the stationary distribution, or the stationary distribution. And if that happens, even if you are sampling at different times, your distribution remains the same. which means all the samples are now from the same distribution, which means all of those samples can be used to represent a distribution. P should not, so basically P is to be designed by you. Yeah, here also it will not be symmetric. No, 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 it will not be identity. It is possible. I can give you some examples, but I have to do maths, not maths, I mean some mathematical example. So it is possible, even without identity matrix, it is possible that these two will remain same always. It's always possible, and it's very simple. Suppose your output pi t is one value is 0.5. So it's very simple. I can always design, right? Because let's say my pi t is 0.1, 0.3, 0.5, not 0.5, 3, 5, yeah, it can be 0.2, right? Now on the other hand, I also want the 0.1 value, let's say at the first value, right? So then I can always multiply it with some matrix such that this will not be 1 and 0, but some proportion of this which will add up to 1. So for example, it can be 0.5 times, let's say 0.05, that will give you 0.25 or something like that. So in the 0.025, and in that case you can find out those numbers which without being 1 it can still give you that result. Can't you find out 4 weights such that this matches? You can always find out 4 weights, right? That's the thing. Okay. In fact, it should not be 1. If it is 1, then this breaks down, because that means you are stuck in one mode. Wherever you are, you will only get that. So it's
multiplication of this matrix and the multiplication of transpose of that matrix. Same matrix. It will be the identity.
Yeah, but that. So no, it is not orthogonal. How is it orthogonal? This matrix is not orthogonal. How will it be orthogonal? They are not matrix, first of all. So, and second of all, you will not get identity. P is not identity. So they are no way orthogonal. Okay. So there is one more concept that is remaining here, which I will do next time. Then I will 5 minutes I will generalize it to continuous, and then go to Markov chain. But that will be after your minor. So I think 18th it is ending. So 19th I think. 18th is Wednesday. So 19th class we will do that. So my suggestion will be, before coming to 19th class, we will forget this. So please go through the video and then come. Okay. Otherwise 19 everything will be like what is happening. So please see this video before coming to the class on 19th. Okay. Thank you.